Welcome to the second session of the day. The first speaker of the session is Schwarz from the University of Singapore, and he's going to tell us about data race detection in the Goblint static analyzer.
Okay, so thank you for the kind introduction. So indeed, today I'll be talking about data race detection by digest-driven abstract interpretation. Throughout this talk, we'll be looking at this example a couple of times, so it may be worth spending some time looking at it. So it's a very simple example program. You see that we have two threads, namely this main thread and then another thread T1. And we have a set of mutexes. In this case, we have this mutex A. And we can initialize this mutex, and we can lock and unlock the mutex. And we also have global variables. For instance, here we have this global variable G. And what this program does is first, while no threads are created, it assigns a value to this G. Then it dynamically creates a second thread. There's namely this thread T1. The first thread then locks this mutex A, assigns a value to G, and then unlocks the mutex again, whereas this other newly created thread also locks the mutex, assigns a value of 12, and then unlocks the mutex. Now, in one of the questions that we might ask ourselves about this program is there a data race in this program? And the classical definition of data race is you say that two accesses in a program race, if at least one of these accesses are right, if they access the same data, and if they can somehow happen at the same time. And in this work, we're focusing on the last aspect of this. So we're deciding whether two accesses can potentially happen at the same time. So let's unpack the title maybe a little bit. We're saying data race detection by digest-driven abstract interpretation. Now this is VMCAI', so I won't spend too much time explaining what abstract interpretation is, but just briefly in case someone is not familiar. So it's a technique that was proposed by Patrick and Radia Couzeau in the 70s, and it works by systematically over-approximating the concrete program behavior. And then if you can show that your over-approximation of the program behavior does not admit the bug or the problem, then your actual all concrete program executions will be safe too. Now, when you apply abstract interpretation naively to multi-threaded programs, you immediately run into a state explosion problem. So this does not really work. So what you need to do is you need to be a little bit smarter in some way, but also less ambitious in another way. Namely, what you want to do is you want to do something that's called thread-modular abstract interpretation, where you try to analyze each of the threads that you have in your system in isolation as much as possible. And this is not completely possible because different threads in your system usually tend to interact in some way. But for this interaction, you decide to go for a quite coarse abstraction of this interaction, so coarse over approximation. So if you think about value analysis, an example may be that you say, okay, for all of these global variables, I just assume that any read that I have in my system can read any of the values that were written at any point. So this is thread-modular abstract interpretation, and what this gives you is something that's usually quite scalable, but also often quite imprecise. And this is then the point where we come to digest-driven abstract interpretation. And we have observed that there's a lot of ways that you can improve the precision of these thread-modular abstract interpretations. And what they usually have in common is that you tend to preserve some part of the history. So you have some history abstraction, and then you take this into account to decide which interactions are actually feasible. So if you think about, for example, about a value analysis, you may say, okay, a thread cannot actually read a value that is written by another thread, which can definitely not have been started yet. Or another instance of this is that a thread cannot read older values that it has written itself if it has definitely overwritten them in the meantime. And then digest-driven abstract interpretation is a principled way of designing these history abstractions. And the nice property that you get is that you sort of you get a separation of concerns in some sense. So you have an analysis that you prove sound, and then you have some requirements on your digests that you need to prove, so on your history abstraction. And the result here is that these compose nicely. So basically, if you come up with your new favorite analysis that aims to be more precise by taking yet another aspect of the history into account, you don't need to start proving your analysis soundness from scratch as long as it follows this principle. So this is some result from 2023. And you can think of these digests in some way as a type of concurrency sensitivity, because they specify which aspects of the thread interactions you want to track and what you want to abstract away. So you can say, oh, in some way it is similar to flow sensitivity, context sensitivity, and all of these other types of sensitivities that people have proposed in sequential analyses. Another helpful way to think about it, especially if you're an abstract interpretation person, is you can see these digests as a generalization of this trace partitioning technique that Xavier Rival and others proposed to a multi-threaded setting. What are examples of such digests? Examples of, for example, are computing the set of held mutexes, where at every program point you track which mutexes you have. Another example would be an analysis of dynamically created thread IDs, where you try to compute thread IDs and maybe also try to determine which threads are unique, so which type of threads are in the system where you only have one instance of them. So this is an example of a very simple digest where I'm computing some type of thread ID. And here I have two different thread IDs. So basically I have a thread ID for the main thread as long as it is single threaded. So as long as it has not created any other threads, we give it this thread ID st main. Then we have empty main, which is also for the main thread, but basically that's its thread ID as soon as it starts creating any other threads. And then all of the other threads, we don't distinguish them. We just say, okay, they fall into this category of other. Now, if I look at our example program again, and I do an abstract interpretation that uses this digest, then I would, for every program point, also have the digest information for it. And in this case, it will always be st main until the main thread goes in and for the first time creates another thread. Then it has this thread ID empty main. And then the newly created thread, this t1, will always have this thread ID empty other. And now if I think back to our value analysis that you might want to do, you might want to ask the questions such as, can this variable r that reads the value of g, can the value of this be 12 after the value has been read into r? And the question here then becomes, is st main in some sense, it does not seem to be compatible. We're back, okay. So the question becomes, is st main compatible with mt other? So this is the question that you might ask yourself here. And if you think about it, so when we are doing these digests to improve the precision of value analysis, we're somehow asking these questions, are two digests compatible? And when we're thinking about data race detection, and especially this aspect of can the access happen concurrently, then our question becomes, can two accesses possibly happen in parallel? And if I squint a little, then I can turn this data question into the question of, can two accesses possibly happen in parallel given their associated digests? And then I see that actually there is some type of connection here. So in both cases, I'm asking questions about these digests. And this was the starting point for this work that I'm presenting here, where we basically wanted to reuse all of this machinery that we have for improving value analysis to answer questions about whether there may be races. So the contributions in the paper, there's a first part that deals mainly with the concrete semantics. So to have nice proofs of our analysis, we have a concrete semantics that is also thread-modular, and we call this local trace semantics. And for this question of races had not been studied yet. So we provide the definition of what it means to be racy in this local trace semantics. One is quite intuitive. The other one is a bit less intuitive, but in some sense it's nicer because, as we'll see later, it lends itself more easily to abstractions. And in the paper, we then show these two definitions of races in the local trace semantics equivalent. What we'll focus on this talk a little bit more is how we are actually using these digests for data race detection. So we will show a technique how you can use any digest that you have to answer questions about which accesses can happen in parallel. We will also see that this generic definition is not always the best one that you can hope for, and we'll provide some bespoke definitions. We will cover the algorithm for digest-driven data race detection that's used inside of the Goblint tool. And lastly, I'll also briefly talk about our experimental evaluation that we did of different digests on the SVComp benchmark suite. So for the first aspect, let's take a look at our example program again. And when we think back to our value analysis, we would say, or we can say that some things are not compatible and others are. So for example, if a thread is st main, then it would only be able to read other values that were written by the main thread. So this is one of the conditions that we can give. And the other one is empty main or empty other can read any other values, can also read things that were written while the thread was potentially, or while the program was still potentially single-threaded. And one way to write this down is in this way here. So what we're doing here, don't be scared off by the syntax, but basically what this says is I'm computing the successor digest given the digest of the thread that's reading and the digest of the thread that performed the writing. And here what I'm saying, well, if I am the main thread and I am trying to read something from some other thread that is not the main thread, this is not possible. So this cannot happen. And then I say here, the set of successor digests is empty. And in the other instances, the successor digest will simply be the digest of the first thread. Because if I am the main thread and I read from some other thread in the program, this doesn't change my thread ID. So this, we have just to introduce the notation. And then let's see how we can get from this to actually the races. So if let's consider a data race between two accesses. And let's say these two accesses have the associated digests A0 and A1. And then the access with the digest A1 can be ordered such that it happens before the access with the digest A0 because they are racy, so they are unordered. And in this case, if I'm reading with the digest A0, or if the thing with the digest A0 is a read, and the thing with the digest A1 is a write, then the read can read the value that was written by this writer. So basically what I conclude from this is I can say if there's two accesses with digest A0 and A1 and they are racy, then in this abstraction here, I say that these digests must be compatible. And from this we can conclude that these digests cannot, or two accesses with digest A0 and A1 cannot race if they are incompatible in this digest world. And now because we have chosen A1 and A0 arbitrarily in the beginning, we can also flip those around. So basically what I can say is two accesses can only ever race with each other if the digests are compatible in both directions. And then this leads us to the definition of this predicate, which is supposed to answer exactly these questions. So I have two accesses with digest A0 and A1, and I want to say, can they possibly happen concurrently? And we write it down like this. So we have this predicate, we give it two digests, and then this predicate will either return false, which says the accesses with these digests can never race or can never happen concurrently, or it will return top, which says, okay, they may not race. So returning top instead of true here is a deliberate choice because we have done an abstraction before. So usually we are not able to say that they will definitely race. We can just say, okay, we don't have enough information to exclude that they will race, which is why we have this top here. Now, we can define this predicate in a generic way by using this insight that we just had before from this bidirectional digest compatibility. So we can say if the digests are not bidirectionally compatible, then we know that there will be no race. So this is this definition here. And if they are bidirectionally compatible, then we don't know anything. Then we show that this definition is actually sound for any digests. And the way this works is that the bidirectional trace compatibility, which we show to be equivalent to the intuitive definition of a data race, implies the bidirectional digest compatibility by the construction of the digest. So this is a proof that you might want to read up in the paper. What this gives us is a way to automatically derive from any digest, a way to check for data races. And the nice thing is this doesn't come with any additional proof obligations. So if I have a digest that is admissible, that I can use in my analysis, then I can also use it to check for data races without having to prove anything else. So let's take a look at our example. So recall we had this program with the single-threaded, with the thread ID digest. And what I've done here is I have basically inlined these definitions that we had given earlier for the trace compatibility. And what this now says is the two accesses do not race if the first thread is the single-threaded, if the thread is single-threaded and in main, then it will not race with anything that is not single-threaded in main. And it also, yeah, so this is but both directions. So this we can already use to exclude some of the races. So for example, we might be able to exclude the race between this axis here, where we set g to 0, and this axis here, where we set g to 12. However, this is also an example of why this generic definition is not always precise enough. Consider, for example, this case here. The single-threaded main thread, single-threaded main thread, according to our predicate here, races with itself, which in some sense is logical that our predicate would give us this answer, because we constructed it from answering questions about, can we read values that were written by this thread? And yes, of course, I can read values that were written by myself before. So this here will give us top, and the same for the multi-threaded, for the main thread in multi-threaded mode. We will also say that it might potentially race with itself. So this is why this definition here is not completely satisfactory yet. And what we actually want is we want to give a dedicated definition here that exploits all the information that we have in our thread ID domain. And for example, this might say the first part says that accesses with thread ID st main are never involved in any races. And the last part says that if both accesses happen by the main thread but already in multi-threaded mode, then they can also not be racy. This is a dedicated definition that captures more of the things you want to capture. The downside here is that, of course, now I will have a manual proof obligation. So now I will have to show that this actually implies that there will be no races. Let's take a look at another example. So this is the lockset analysis and the lockset digest. And there probably people will agree that if the locksets that you hold at the two axes have a non-empty intersection, then they will not race, because they're somehow protected by these mutexes. And this is what the predicate here gives. And this is once again an instance of this dedicated definitions that we have. And then we might want to actually show that this definition is sound for the lockset digest, and I'll give you a flavor of what a proof of this would look like. And the proof here would look like that I say two axes if you have two axes that hold a common lock, let's call this lock A, for example, they are ordered with respect to each other by the locking and unlocking operations for this mutex A. And then what you have is that one axis sequence must happen before the other axis sequence, and I cannot flip them around, and therefore they are not bidirectionally trace compatible. So this is the type of argument that you need to make here when you want to show one of these custom predicates. Now, something that will also immediately be obvious to an abstract interpretation audience is we have several of these things. Let's maybe try to combine them, and this here is an easy way to combine them. You can say, okay, if one of the digests that I have can exclude that they can race, that this is good enough. So it suffices if one digest can say this. And if both say, I don't know, then we also need to say, I don't know. This, in some sense, is a bit like an open product. The nice thing about this definition here is that it's once again sound by construction. And then the reviewers already asked, okay, but this is sort of boring. Why don't you do a reduced product? And yes, this is a good point. We can also do a reduced product where we try to exploit more of the information contained in the digest, and maybe also use the information from one digest combined with the other digest to finally conclude that there's no races. The downside with this is, whereas for the open product it was somehow sound by construction, for this reduced product we need to actually make a proof. But it's actually also helpful, and we do use it, for example, in the Goblint system. We use it when we are combining thread ID information with set of must join threads. Okay, so then let's maybe show what our data race detection algorithm in Goblint actually does. So this here is our typical starting step of an abstract interpretation. We construct our constraint system. We do this by supplying the program, the digest, and then your transfer function of usual abstract interpretation. This gives you a constraint system. To this, we add an additional unknown where we will accumulate all of the accesses to a given global. So if you have an extra unknown RG, and there we collect information about all accesses, then we give it to a fixed point solver, whichever fixed point solver you like. And what this fixed point solver at the end gives us is a solution. And then we iterate over all of the accesses that we have accumulated. And basically for all of the accesses, we check, well, is one of them a right? This is this line down here. And if at least one of them is a right, and our nice predicates cannot exclude that they may race, then we actually report the race to the user. Let's take a look at our example again. So during this accumulation of accesses, we may find that we have an access in this line 2, which is a right, and then we have the digest information that's associated with this, so main thread in single-threaded mode and no lockset. And we do the same for this other access in line 6 and the access in the other thread. And after we have computed the result here, we then go in and try to check pairwise whether these things may race. And we first start off with this st_main, and we check whether it may race with itself. Now we have refined the definition of this predicate. So here we'll say, okay, main will not race with anything. So for all of them, we will find that they will not race. So this access cannot be involved in any data races. Then we continue with empty main. For empty main, we also said it does not race with itself. So this is also safe. Then when we consider this pair here, we see that the thread IDs are not enough to exclude that they may race. However, here I have a non-empty intersection of the lockset. So those two are also safe. So is this one. And then lastly, I consider these accesses empty other. And there I find that the thread IDs, once again, don't suffice to exclude the race. But we have, once again, this non-empty lockset intersection. So then I would conclude for our fabulous program here that is actually race-free. Now we have experimentally evaluated these things within the Goblint static analyzer. And actually this digest-driven abstract interpretation provides the semantical foundation in some sense for what this Goblint system has been doing for a long time. And this Goblint system actually was winner in the data race categories of SVComp in 2021, 2023, and 2024. Now we look at 2025, which it didn't quite win, but it's the most recent one. So the benchmark set in SVComp consists of about 800 race-free programs and about 250 racy programs. And it's a mixture of regression tests and tasks that are extracted from real-world software. If you look at the tools that competed and got a significant score in this category, then we see that Goblint here is the only tool that did not produce any false negatives. And also the overall number produced by the tool is quite impressive. And this cooperating tool here actually also incorporates Goblint as one of its components. So this is not quite a fair competition. So the question that we then asked ourselves, okay, which of these digests that we have in the Goblint system are actually responsible for these results? And we have the following digests. We have this lockset digest that we've seen before, extended with support for reader-writer logs. We have this TF, is the simple thread IDs that we have just seen. We also have some more advanced thread IDs, and we also have some analysis of mass-joined threads. And then we have a bunch of things that came out of specific papers. And then when we evaluated the results, we found that for 15 tools, we needed none of the digests to show that they were race-free. So basically, these tests only contain atomic variables. So they are not that interesting. On the other hand, we saw that each of the individual digests, they sometimes move the needle a little bit, but to actually get impressive results, it is the combination of both of these things. So the conclusion is here that for the tasks that you have in SVComp, you need a combination of lockset reasoning and thread reasoning to show race freedom. And the last thing is maybe also a bit depressing. If you look here, these very specialized techniques that colleagues of mine came up for their papers, they don't matter so much on these benchmarks anymore. So we already get 681 without these specialized things, and then they only add a few more. So what we have seen here is we have seen the definitions of race for this local trace semantics. We have seen a framework to check for races using this digest-driven abstract interpretation. We have seen how we can automatically derive this predicate to basically benefit from any digest that your analysis implementers have provided. And we have seen that sometimes you might want to do bespoke definitions. And we've also seen a little bit of the experimental evaluation on this SVComp benchmark set. And with this, I'd like to thank you for your attention, and I look forward to any questions you may have.
All right, we have 5 minutes for questions. Any question?
So thank you for your talk. I was wondering, so you showed that the more the digest, the better the precision. How expensive is the combination of all those?
So this is a very good question, and we have to admit to our shame here, we did not evaluate how expensive these combinations were. So in our experiments, what we did is we basically always enabled the digests, and then only for the post-processing we turned some of them off to see what their impact was. Now potentially they can be somewhat expensive because what we get is an abstract interpretation that is sensitive in this digest. So if you imagine a digest that has 10,000 disjoint values and you encounter all of the program points with all 10,000 values, then you get an immediate blow up. In practice, we have not seen this blow up, and I think for these tasks, I don't have the exact number in mind, but I think none of the tasks took longer than 30 seconds to analyze. Does that answer your question?
Another question, maybe? Don't be shy. So I have one.
Sure.
Can you tell us more about the assumptions on the memory model that you made so that your analysis is sound?
Yes. So this is a very good question. So our assumption for the memory model, so there's two parts to this question. So we have a hosting abstract interpreter, and this hosting abstract interpreter, you can confine it, you can configure it with different types of analyses. So we have non-relational analyses, and for these, we have shown it to be sound for sequential consistency, but it should also be sound for some weaker types of memory, because basically our abstraction is coarse enough in some sense. If we go towards, you can also enable relational abstract domains, and these relational abstract domains also, so they sometimes infer non-reachability, and this leaks into the race detection thing. And because sometimes a program point, your base analysis will say, oh, it's completely unreachable, but this is actually under the assumption of sequential consistency. So if you configure it with relational domains, then you actually need the sequential consistency. Then for weaker memory models, we will be unsound.
We have some time for one quick question. Well, if there's none, then we can thank Michael again.